The magnitude of torque is given by the product of force times radius times the sine of the angle. Torque is enhanced by increasing the force, increasing the radius of the lever arm, or making the angle between them perpendicular. Positive torques act counterclockwise about some point, and negative torques act clockwise. For an object to be in static equilibrium, two conditions must be met. The vector sum of the forces must be zero to prevent any linear accelerations, and the vector sum of torques about any point on the object must be zero to prevent angular accelerations. The model arm used in this lab simulates the action of the biceps muscle on the forearm. The biceps attaches to the forearm a short distance from the elbow joint. Contracting and relaxing the biceps muscle allows the forearm to be raised or lowered. Our model has a solid rod upper arm that can be locked in place at various angles, a wooden forearm with a pin at the elbow joint, a string with upward tension to represent the biceps muscle, and a load attached at the far end of the forearm. A force sensor allows us to measure the tension in the biceps. In the first arrangement, the upper arm is at right angles to the forearm, giving the biceps a nearly perpendicular angle to produce a large amount of torque with minimal tension. Let's examine a free body diagram of the situation where the forearm is horizontal. The tension in the biceps, T, acts at a distance d sub t from the elbow joint at an angle theta to produce a counterclockwise torque. The distance d sub t can be measured from the elbow joint to the point where the string attaches. The weight of the forearm acts at the center of gravity of the wooden forearm with a perpendicular angle to produce a clockwise torque. The center of gravity is at the middle, but its distance from the elbow joint is slightly less than half the length. Figure out where the middle of the forearm is and then measure the distance to the elbow joint. The load produces a clockwise torque at a distance d load from the elbow joint to the point where the load is attached. The x and y components of Rx and Ry of the reaction force of the elbow joint on the forearm doesn't produce any torque about the elbow joint itself, so we will ignore this force. Summing all the torques about the elbow gives T times d sub t times the sine of theta minus W arm d arm minus W load d load, and these should sum to zero. At some point you will need the mass of the forearm. Here is the step-by-step assembly of the apparatus. Calibrate the force sensor in the usual way using a 500-gram weight and calling it 4.9 newtons. Make sure that the force sensor is able to swivel to point directly along the direction of the string tension. Take a moment to level the forearm horizontally by comparing it with the wall blocks in the background. Use a protractor with the string passing directly through the central hole to determine the angle theta. In Data Studio, drag and drop a digits display onto the force sensor and adjust the number of digits behind the decimal to 3. Clicking the Start button yields the tension force in the string. Calculate the net torque, which should be nearly zero. Compare this small residual error in measured torque with the total counterclockwise torque due only to the biceps muscle to get a % error. Use the data shown and the same approach to estimate the tension in a real biceps muscle. Now angle the upper arm while keeping the forearm horizontal and repeat the experiment. The biceps muscle now acts at a lower angle, so you might expect more tension to be needed. Finally, place the biceps in a contracted position and repeat the experiment. The free body diagram now becomes slightly more complicated in that the weight of the forearm and the load act at the angle B relative to the forearm. The clockwise torques now involve the sine of B. A protractor can be used to measure the angle theta, and a protractor or goniometer, shown here, can be used to determine the angle B. For architects and mechanical engineers, the bridge or catwalk is an important structure. The supports at either end of the bridge must balance the weight of the car and bridge, but also prevent torques. In this lab, the bridge consists of a 1-meter stick supported by 2 force sensors and a load placed on the bridge. A free body diagram of the meter stick includes the upward forces of the 2 supports, the weight of the meter stick, and the weight of the load. The sum of the forces is just F1 plus F2 minus the weight of the stick minus the weight of the load. The sum of the torques about the 0 centimeter end will be F1D1 plus F2D2 minus W stick D stick minus W load D load. You will need the weight of the stick. The hook may be unscrewed from the force sensor to give a flat surface. Two force sensors will be used and must both be calibrated. Calibrate them in the upward position, placing a 500-gram weight on top. After calibrating the first sensor, go to the top of the calibration window and select the second force sensor, repeating the calibration procedure for it. Drag and drop digits displays onto each force sensor and push the start button to measure the two forces. Obviously, you expect more force on the sensor closest to the load weight. Add the upward forces and subtract the downward forces to obtain the nearly zero net force. Divide by the upward forces to get a percent error. Add the counterclockwise torques and subtract the clockwise torques to obtain a nearly zero net torque. Compare the net torque with the counterclockwise torques. A diving board and a cantilever are similar objects. The only upward force here creating counterclockwise torque about the left end is the support F2. The downward forces producing clockwise torques are the load, the weight of the board, and the downward pull of the support F1. Here is our model cantilever, using one force sensor aimed downward and the second sensor directed up. The load is placed beyond the second support. Since the first sensor is aimed downward, a negative sign is introduced for the force F1. Otherwise, the analysis of the torques and forces remains the same. You'll need to recalibrate the first sensor since you have inverted it and put the screw back in place. Start with no weight, then hang 500 grams, but fool the calibration program by calling this hanging weight minus 4.9 newtons. This way, upward pressure on the force sensor will be read as positive values. Place the first force sensor at the 10 centimeter mark, the second sensor at the 70 centimeter mark, and the load at the 90 centimeter mark. Check to see that the sum of forces and torques are zero.